So my name is Shudong Zhou. I'm a senior engineer at VMware. I've been working in the networking area for about 4 years at VMware. So there's no keynote this morning, so you're stuck with me for the next hour. I'll be covering some of the basic concepts in the vNetwork, which is a marketing name we give for all the networking support for virtualization in the VMware products. And it's not going to be a tutorial. It's more of a, the basic concepts and some of the things you should be aware of. If you want to know exactly how to do certain things, there's obviously the various configuration guides, and there are separate sessions going into the deep dives of the specific areas. So this is a standard disclaimer that you probably have seen dozens of times already. So I'm going to start with the basic concepts, and then I'll cover so what are the key choices you have. We basically support 3 types of virtual switches. You can pick and choose based on what suits your needs. And I'll cover in terms of what aspects you need to consider when you make the choice. Now I'll cover some of the best practices. Now just to bring things out, typically a good number is 3. So I'll cover 3 key points. There are some additional considerations, mostly relevant to not just how you set up the virtual side of the networking, but how the virtual side goes with the physical side, and how to make sure that you don't have mismatches between the virtual networking and the physical networking. Now, just in case you fall asleep, I just want to cover the 3 key points that I'm going to cover. And if you get nothing else, you should at least get these 3 points. So the first point is that when you configure your virtual network, you need to keep the infrastructure traffic separate from the VM traffic. Right? So I'll cover specifically how you would separate them. So there are typically 2 ways you do it. One is you have separate physical adapters or separate networks, right? Where you send your VM traffic into one network and you send your infrastructure traffic into another network. Now, that's going to take more physical infrastructure to do that. The other way is you separate them through VLANs. You put infrastructure traffic on a set of VLANs, and then you put your VM traffic on a separate set of VLANs. So they can share the same physical wire, physical switch, and physical network. So that's the more common practice today. The second point is you always want to use NIC Teaming. Right? So by that I mean when you construct a virtual switch, you always want to connect more than one pNic, 2 or more pNics onto the same switch. And these 2 pNics should be equivalent in be able to carry all traffic that's going on that virtual switch. And so the advantage is that if one of the pNics fail, then you still got the other physical adapter to cover you. And the second thing is that you can do load balancing, right? It's not like you're wasting one of the physical adapter. So always remember that. I think for those who are pretty experienced, that's a given, right? But just in case, I want to emphasize that. The last point was really something new that we have introduced in vSphere 4.1. And that is called network I/O controls. I think Steve Harold covered a little bit of that very briefly in the keynote yesterday. The key idea is that 10 gigabit Ethernet is now very popular, right? It's actually, in getting into more and more sites. With 10 gig Ethernet, you have enough bandwidth to cover all the traffic in your virtual, for virtualization. So not just the normal networking traffic from your VMs, you can also use a 10 gig is sufficient to cover your VM traffic, your infrastructure traffic. By infrastructure traffic, I mean the traffic that's required to manage ESX hosts, the traffic required for your storage, right? So if you use iSCSI, NFS, or FCOE for your storage traffic, you can basically get rid of the storage adapters and put everything onto your Ethernet. And Net I/O control gives you the tool to separate different kinds of traffic so that you don't run into a situation where if you have a burst, say in the vMotion traffic, suddenly it takes out your storage or something like that. So it gives you the tool to separate them out, to really take advantage of the 10 gig Ethernet and reduce the wiring requirement in your data center. So these are the three key points. Okay. So I'm going to start with some of the basics. So and then slowly move toward and elaborate on the three key points that I just mentioned. So this diagram shows what most people already know, but I just want to reiterate in case for people who are new. So this diagram lists the basic anatomy of an ESX host for the components relevant to networking. Now, the key point of having virtualization is you want to run the apps, right, on multiple apps in the same machine. Okay. So on the top left side, you have 4 virtual machines running different apps, and each virtual machine is going to have a bunch of 1 or more virtual adapters. Okay. Now, what virtual networking is about is to be able to support the network traffic between the virtual machines. Okay, that's really the key goal, is that you want to provide the network service so that the VMs can talk through the network as if the VMs are running on a physical host. Right? And the way we support that is by providing an abstraction called a virtual switch. Okay, so for all the VMware, the vSphere products, you have to have some kind of virtual switch implementation in there. And the goal of this virtual switch is to be able to forward traffic between the VMs on the same host, as well as for traffic going out of the VM, out of the wire to some other VM in a different host. Now, in addition to the VM traffic, the virtualization has got sufficiently complex that there is other traffic going on. So one type of traffic is we have a service console, which is used to manage the host, the hypervisor itself. So there is a fair amount of traffic going on between the service console and the virtual center and other entities in the vSphere infrastructure. So we also have called a VM kernel, what we usually call VMK-NIC. So this is a virtual NIC that's used by the ESX kernel to communicate through the network. So for example, if you have NFS, right, if you have NFS storage, then the NFS storage is the host contacts the NFS storage through the VM kernel TCP/IP stack. And the kernel TCP/IP stack cannot talk to the physical adapters directly. It has to talk through a virtual adapter, then through the switch, then talk to the entities outside the network. And that's basically by design, that nothing talks to the physical network, the physical adapter directly. Everything goes through one kind of virtual NIC or another. So beyond these virtual adapter entities, so we have the virtual NIC that belongs to the VM. We have a VMK NIC that's used by VM kernel for infrastructure traffic. And we have management, a service console, we usually call the vSwift, used by service console. Now, notice that the service console does not only exist in the classic ESX. It does not exist in ESXi. So in the case of ESXi, all management traffic goes through VM kernel NIC. Now, there's also, besides the virtual NIC and the physical NIC. So the physical NIC obviously is in order for the host to be able to talk to the outside world. There's a concept of a port group. So what is the port group? Well, the port group is an abstraction of how a specific virtual NIC is going to communicate with other virtual NICs and physical adapters. So for example, the very first decision that you have to make, say you have traffic coming down this VM, and the destination does not reside on this host. So you're going to send this traffic out through some physical NIC to the outside. But you have 4 physical NICs, which one are you going to pick? Right? Obviously, you cannot send it out through all 4 uplinks because then every packet will be duplicated 4 times. You don't want that, right? So you have to have a choice. And that choice is encapsulated in that port group. Okay, so the port group includes a policy which tells how the vSwitch is going to select a specific physical adapter to send traffic out. So obviously you can, for different VMs and different VNICs, you're going to potentially pick a different pNic to spread traffic across here. So besides this is what we call the teaming policy. And then besides the teaming policy, we also have other policies like the port security. So one example is, do you allow the VM to forge its own MAC address? That is, are you going to allow traffic where the source MAC address does not match what the VM claims it started out with, right? And so that's important in certain secure environments. And there are actually reasons you want to allow forged MAC address. For example, if you want to have a MAC address that does not start with the VMware OUI for licensing reasons or for whatever else. So this port group is sort of everything you need to know about networking is encapsulated in there. And typically you have someone who is familiar with networking to set up the port groups. And once you set up the port group, you just tell whoever deploying the VM to say, okay, go connect to this port group. So the VM admin does not need to know the details of how exactly a port group is being set up. So this is a key abstraction in how we set up the networking. Besides these, and we also have the concept of uplinks, which is the connection between the physical adapter and the physical switch. And in many cases, we use the concept of uplinks interchangeably with the physical NIC. Because given a physical NIC, there's a one-to-one correspondence between a physical adapter and the uplink. And obviously, you have to have physical switches in order to communicate between the various ESX hosts. So here is a text representation of what I just talked about. I think there's, just to repeat, there's a concept of virtual NIC, VMK NIC, and vSwift. And basically, vSwift only applies to the classic ESX, does not exist in ESXi. Then you have the physical adapter. and we often call it pNic as opposed to VNic. This virtual switch is one of the key components, and it's responsible for forwarding packets between VNics, VMKNics, and pNics. And then you have the concept of the port group, which is a group of ports sharing the same configuration. And then you have the uplinks and NIC team. So that covers all the basic concepts. So as you read all the various manuals and articles, you'll be encountering these terms. So next, I'll talk a little bit about the choices of the virtual switch you have. So there are basically three types. The first type is called a vNetwork standard switch. So the standard switch comes by default. So every time you install ESX, a standard switch is automatically created for you on the particular host. And you don't need, you can create additional instances of standard switch. And so one of the key thing about the standard switch is that it's created and managed on a per host basis. So if you want to change something, you have to go to that host, go to the specific host, and to change things. And when you change the specific instance on the host, nothing else on the other hosts are impacted. And if you want to keep things consistent across different hosts, then you have to iterate your procedure across every host. And that can be a cumbersome process if you have lots of hosts. The standard switch support basic features such as VLAN and NIC teaming and port security. So which is, for the majority of the simple use cases, that's sufficient for covering all the needs. The second type of the switch is called a distributed switch, abbreviated as VDS. The primary difference between VDS and VSS is that the VDS is created and managed at the vCenter level. So you have a vCenter that's controlling a whole bunch of hosts, and you create a single logical switch at the vCenter. Then you add particular hosts to that VDS. And so basically, this is the VDS is a distributed entity that spans any number of hosts of your choice. Okay. The restriction is that all the hosts must be controlled by the same vCenter. You cannot span VDS across multiple vCenter. So VDS supports all the features that VSS supports and plus more. Okay. So for example, it supports private VLAN, which is a variation of the normal VLAN, with some twists. It also supports traffic management, which is another term for, it's mostly net I/O control, but we also have some additional ways allow you to restrict traffic from a specific VM, basically a shaper, a traffic shaping implementation. So one thing to note that the standard switch and distributed switch actually share the same VM kernel module, switching module in VM kernel. The only difference is that the control path is different. In one case, in the case of VSS, it's controlled, all the controls and settings are persisted on a per host basis. So if you change one host, it only impacts that host. Whereas in the VDS case, it's controlled from the vCenter. So if you change the setting on a particular port group, it's automatically propagated to all the hosts that's part of that distributed switch. Now, the last choice that you have is an implementation that's delivered by Cisco. So what happens there is that the kernel switching module is completely replaced by a Cisco implementation. Basically, Cisco wrote fresh code, and the Cisco module decides how to forward the packets from one virtual NIC to another, or to forward traffic between the hosts. And it's created and managed not from vCenter, although the vCenter is still required. It's created, it's managed through a VSM, which is called a Virtual Supervisor module. Now, this Virtual Supervisor module is an application that can either run inside a VM, or it can run on top of a separate hardware. So Cisco actually ships a hardware box called the Nexus 1010 that can be used to control one or more instances of Nexus 1000V. And the Cisco Nexus 1000V supports features typically available in Cisco hardware switches. So the interface is very much like a normal iOS CLI. In a way that if you're already familiar with the management of physical switches, you should feel very much at home when you try to manage the Cisco Nexus switch. So here is a rough comparison of the various features. And so obviously, all the switches support VLAN and some form of port security. They all support multicast. In terms of linker aggregation, or Ether channel or port channel, both the VMware standard switch and distributed switch supports static Ether channel, but does not support dynamic link aggregation negotiation. Whereas a Cisco switch supports LACP, which is a dynamic form of linker aggregation. So in addition, like Cisco switch also supports SNMP, NetFlow, and other features that's typically available in the physical switch. But VSS and VDS currently do not have such support. In terms of management, the VSS and VDS are managed from the vSphere client. You connect it to the vCenter and you manage from there. And the Cisco switch is managed from the Cisco CLI. You cannot manage it from the vSphere UI. So obviously, this is a rather incomplete table. You should refer to the specific release document for the full set of features that's supported. Now, before I leave the subject, I want to just give a few guidelines to help you pick what type of switching solution you should be using. There are a number of factors that you can consider. The first one is size of your deployment. So if you have only a small deployment and doesn't really require any fancy networking features, then the standard switch should be sufficient, right? If you have like 3 or 4 hosts, if you want to change anything, you want to go through every host and just go and tweak your parameter, or you can automate that somewhat through scripting. But if you have a large deployment, if you have dozens of hosts or even hundreds of hosts, obviously going through that is going to be difficult. You can always script to get around it, but there are always exception cases. Someone who had a problem go and change a setting over the weekend without telling anybody else, then now you have something that's inconsistent across different hosts. So in this case, you should consider using distributed switch or use N1K, the Cisco switch. Okay. What that guarantees is that if you make a change, the same change is going to apply across all the hosts. That's part of the distributed switch. There are also organizational considerations. Right? So if you have a group which controls both VM deployment and network provisioning, that is, you just have a single group that wants to have control over pretty much everything. Then you can basically, because the VS standard switch and distributed switch allows you to control everything from the vSphere UI, and that provides a natural place, an integrated place, so that you can control both the networking side and the VM deployment. Now, if you have a separate network administration group that's trained on the Cisco CLI, obviously the networking group is going to be reluctant to go and learn a separate graphics UI that they're not familiar with. So typically they're going to demand to have something that they are familiar with, and in most cases the organization are going to be leaning toward picking the Cisco CLI. Now, besides the size of deployment and organizational issues, obviously there are other factors. The first factor is money, right? So the distributed switch and Nexus, the Cisco switch requires the Enterprise Plus license, which is more expensive than the other SKUs. In addition, there are certain features that you might need if you need private VLAN. Obviously, you need at least either the VDS or the Cisco switch. The standard switch does not provide that. So in general, I just want to make a statement that in terms of our development, we are all the features associated with the standard switch are pretty much frozen. And we're putting our efforts into the distributed switch to make it scalable and as well as feature-rich. I think the primary reason for us is that the limited resources where, if you have to do a single feature multiple times across multiple control paths, it's actually a fairly significant amount of effort. So that's all I want to say about the switching, the choice of switches. The next thing I want to go through is the best practices, which is I want to go into a little more detail about the 3 bullet points that I talked about earlier in the beginning of the talk. So first, you want to separate the infrastructure traffic from VM traffic. Now, there are 2 main reasons that you want to do that. One is that you don't want to accidentally leak infrastructure traffic to the VMs, right? So, for example, if you have vMotion going on, so what the vMotion traffic carries are the actual memory content of the specific VMs. You don't want other VMs to be able to snoop on the memory content of the VMs they are not supposed to know about. So you want to keep them separate. And without doing that, that's a potential security violation. There are certain types of infrastructure traffic that's very bursty. So for example, vMotion traffic. While vMotion is going on, it can take up to gigabits of bandwidth. And you don't want the sudden burst to basically impact your VM traffic. So there are 2 ways that you can separate the traffic. One is by using separate physical networks, and the other one is by using separate VLANs. So I'm going to show you 2 examples here. So here's an example of using separate physical networks. So in the bottom here, you have a VM network and you have a management network. And inside, for these two physical networks, we create one vSwitch for each physical network. So they have vSwitch 0 for the management network and vSwitch 1 for VM network. And then we assign two physical NICs to each physical network. So remember, we never want to have just one physical NIC. That's really bad, right? That's what we talked about earlier. So in order to just as a very simple example, say you have 3 VMs, you create a single port group. Say all the VMs require similar setting. So you create a single VM port group and connect all VMs to that port group. And then you create a single management port group and connect your vSwift and VM kernel NIC to the management port group. And basically, that's it. And you should be able to keep all the port group policies as default, in which case it'll do the proper load balancing and failover settings, and then you are done. Okay, so you should be able to just get up and running with this simple setup. Now, here is an example of how you would separate traffic using VLAN. So in this case, you have a single physical network. And the physical network admin tells you that there are 3 VLANs available, VLAN 10, VLAN 20, and VLAN 30. And so what you do is you trunk all 3 VLANs to the physical NIC. Okay? So that's a setup that you have to do beforehand. So once you have all the VLANs trunked to the physical adapter, then you create a single vSwitch, okay? And then you create a port group for each of the VLANs available to you. Okay. Now you create a service console, you connect your service console to VLAN 10, and you connect your VMK NIC to VLAN 20, okay? And then you connect all your VMs to the VM network, which resides at VLAN 30. So basically, now you have separated the traffic in terms of VLAN. Now, in addition, when you set up the port group, you can specify an active physical adapter and a standby. So what that means is that normally, when everything is running, the traffic is going to flow through the active adapter. So in this case, both the service console traffic and the VM kernel traffic is going to go through VMK NIC 1. And all the VM traffic is going to go through VM NIC 0. Okay? Now, if any one of these physical NIC fails, then all traffic will go through the other physical adapter. Okay. So basically, if nothing fails, you effectively separated the infrastructure traffic from VM traffic. But if anything fails, then you still got your backup. So nothing breaks, but you'll be running a suboptimal configuration. So that's on the separation of the traffic. So next point I want to make is always use teaming. Okay. So in a nutshell is you always want to connect 2 or more physical adapters to a vSwitch. Okay. Preferably you want to connect these separate physical adapters to separate physical switches. Right? The reason for that is if you connect both adapters to the same physical switch and the physical switch fails, or if for some reason you need to reboot the physical switch, then suddenly your VM would lose traffic. Right? And you don't want that. Typically, you just use the default setting unless you have special needs. So I'm going to cover, in addition, later on, talk about how you would do the load, set up the load balancing policy. So in terms of there are a few rules that you need to remember when you set up the teaming. So the first thing is all team members, that is all the physical adapters are equal, right? You cannot have a physical adapter that's trunked with VLAN 10 and the other one that's trunked with VLAN 20 and you form a team, because they are not a team. If you have VLAN 10 traffic going through one pNic, it's not going to be able to go through the other pNic, right? So all the pNic, all the members has to be equal. They have the same set of VLANs has to be trunked through both, and they have to be connected to the same physical network, so that if you send a broadcast packet out, all the pNics should be able to receive the same traffic, same broadcast traffic. Now, the other thing is that each port group, when you set up port groups, each port group, it will have its own set of active and standby uplinks. Okay? So when the active uplink fails, the first standby uplink is going to fill in. So say if you have 4 pNics, you set up a port group with 2 active uplinks and 2 standby. And one of the active fails, then you're going to use 1 active and the first standby. And if both active fails, then you'll be using both standbys. So that's how the active standby works. In terms of load balancing, okay, you have several choices. If you're using the distributed switch, we recommend you use the physical adapter load-based balancing. So in this case, we dynamically adjust the choice of the pNic so that your traffic is always evenly balanced. So I'm going to cover that in the next few slides. The second choice is the port ID or virtual switch MAC based. So this is a static assignment. So you take a port ID or take the virtual MAC address, you hash it to one of the active uplinks. And while the VM is alive, you're always going to use that uplink. So this thing basically works in a statistical fashion. So if you have several VMs and you use the hashing algorithm, statistically, some VM will use one uplink, other VMs will use a different uplink. So you statistically balance all the VM traffic across uplinks. The third one is IP hash. So in this case, the choice of the pNic is based on the actual connection. So based on the source and destination IP address. So the same VM can potentially use multiple physical adapters to send its traffic. And the last one is called explicit, which essentially there's no load balancing whatsoever. It just picks the very first physical adapter that's available. If that one fails, it's going to use the next one, and so on. And there's very little reason that I should use the explicit choice. So let me just go through each of these load balancing policies in a little more detail. So the first one, at least from the user perspective, is the simplest one. If you pick the load-based teaming policy, what happens is that we're going to pick an outgoing uplink. That's the outgoing uplink for a particular VNIC is dynamically adjusted based on the current load of the physical adapters. And we currently evaluate the load at 30-second intervals. And so at any given point, if none of the pNic is saturated, then we don't need to do anything, right? Because they all can run properly. Now, if we detect, say, one of the pNic is saturated, for example, suppose this third physical adapter is saturated, then what we're going to do is we're going to adjust and move the traffic to the fourth pNic. And then after obviously we do a evaluation to see, we do the accounting in terms of how much traffic on a given pNic is coming from a specific VNic, and we do the adjustment so that after the adjustment, none of the pNics is saturated anymore. Okay. So you don't have to, if you set this teaming policy, you don't need to worry about anything. We'll do our best effort in terms of balancing out the traffic across all the pNics. Okay. So that's the recommended one if you're using the distributed switch. There's no special requirement on the physical switch setup. It's very straightforward. The second choice is NIC Teaming based on originating virtual port ID. So this virtual port ID is actually an internal entity where it's a number we assign to the internal port of the virtual switch. So in this case, it's a static choice. The outgoing uplink is chosen from a hash of the originating port ID. I think the hashing based on the originating virtual MAC is similar in nature. So basically all the traffic from VNIC will hit the same VMNIC until a failover event. A failover event is basically when one of the pNICs goes down or something like that. So in this case, the return traffic will always follow the same path. That is, if this VNIC goes through this physical port, then the physical switch is going to learn about the source MAC address. And so when the traffic returns from physical network, it's going to follow exactly the same path. Okay. So we depend on the physical switch being a learning switch. So here is just an animated example of how we pick how we hash and pick the physical adapter. So typically, the originating virtual teaming based on originating from virtual port ID is our default, and there's no special requirement on the physical switch side, and it's going to it's the simplest way for you to do the load balancing and teaming. And so unless you are using VDS, in which case you use you should pick the load-based teaming. Otherwise, you should pick this one. Okay. So the last one that I'm going to touch on is the IP hash. So IP hash is used a lot in the field, and I think surprisingly there are actually not very rare cases where you need to use IP hash-based teaming. And the only reason that you want to use this is if a particular VM is really heavy, has a heavy load, such that you're going to saturate a single physical adapter. And typically, you're not going to have that many VMs that's going to use more than a gigabit of bandwidth. The average VM uses up about 5 megabits of bandwidth. So here's how the IP hash works. So you're going to choose the outgoing uplink based on the hash of the source IPN and destination IP. So for example, if you have 3 potential IP destinations and you want to make a connection between this VM and this destination, then based on the IP address X and A, you're going to hash to this particular pNic. And say if you want to connect to a different host, now this time you are actually picking a different adapter. Okay. So the choice of the physical adapter is made on a per connection basis. So obviously, if you only have a single destination, IP hash is not going to help you at all because it's always going to hash to the same destination. the IP address does not change, so you always map to the same adapter. Now, a few things that you need to know. One is that when you configure IP hash, the physical switch must configure static Ether channel. Okay, so for standard switch and VDS, we don't support LACP. Okay, we don't support dynamic negotiation of the link aggregation. So what that means is that suppose you have multiple pNics connected to separate physical switches, then you happen to set up IP hash, and then you require Ether channel, static Ether channel, across two switches. Now, in order to have Ether channel across two switches, then you are going to need multi-chassis Ether channel, which means you have to spend more money on the physical switches. You know, most physical switches don't support you cannot do Ether channel across multiple switches. You have to pay extra money, to get that feature. The other thing I just want to mention here is that you can have failovers and standby uplinks in this configuration. So once you build an Ether channel, you have to put all the pNics in the Ether channel, and then basically because the physical switch side is set with static Ether channel, you cannot dynamically kind of fail over some standby pNic into the Ether channel. A pNic is either part of the Ether channel or it's not. It cannot be dynamically adjusted without LACP. And the other thing is you cannot turn on beacon probing. So the reason is that in beacon probing, we require that a broadcast packet sent out of the pNic the physical switch has to reflect back on the other pNics. But if you configure Ether channel, that reflection does not happen. So always remember, no failover, no beacon probing. Okay? Yes? Can you repeat that? We do actually violate what?
It does actually fail over.
Fail over, you mean? Let's take that offline. I think, yeah. I think it's not a straightforward topic, so maybe we can take it offline afterward. So the question of was the failover aspect of when you configure the Ether channel. All right. So the last one, which is new in the vSphere 4.1 that was released last month. So the idea is that if you want to converge your network and storage onto the 10 gig Ethernet, you can actually do it reliably now. The main reason is that you want to reduce your cabling requirements. And just to illustrate the point, here's one of the pictures of a data center to show that cabling can be a problem. Okay. So you want to, by using 10 gig E, that you basically just remove all your storage adapters, and you basically come down to a pair of 10 gig Ethernet switch. And there are two things that you can use to manage your traffic. One is called a traffic shaping. And this can be used to limit the amount of traffic a VNIC can send or receive. The other one that's a little more useful, it's more interesting, is the network I/O control. And it can isolate different traffic classes from each other. And for each type of traffic is guaranteed a share of the physical NIC bandwidth. And unused bandwidths are automatically distributed to other traffic types. So that's kind of the gist of that. And here's an illustration where traditionally you have a whole bunch of pNics, 1 gig E NICs, that's carrying different type of traffic. Right? And with 10 gig E, then you basically converge it down to a pair of 10 gig E links. And here is an experiment that shows how the network I/O control helps you. So this red line shows a benchmark running. So here the flat part is the steady state. And while the benchmark is running, you run some background vMotion traffic. That is, you vMotion some unrelated VM, which also runs on the same host. Same set of hosts. So if you don't have the network I/O control, then during the vMotion here, you see a dip in the benchmark performance. Okay, it's about a quarter drop here. If you enable network I/O control, you see that during the vMotion, there's no impact at all to your benchmark performance. And here is a sort of a illustration of the actual traffic bandwidth that's being used. So this blue line is the total amount of traffic, and this red line is the vMotion traffic. So on the left, when without network I/O control, during the vMotion, you see a sudden jump in the vMotion traffic, and the rest of the traffic down here, you see a dip. Right? Basically, vMotion is now impacting all the other traffic that's running there. Now, if you turn on network I/O control, you'll see that the jump in the vMotion traffic has been constrained, and there's no impact on the rest of the traffic. So that's the power of the network I/O control. Just to go a little bit deeper into what's available there, how you would set it up, right? So basically, in this case, you have a pair of 10 gig E NICs, so you use different VLANs for for VM traffic and infrastructure traffic. And you want to enable load-based teaming, and you want to enable network I/O control. That's a single button at the vCenter level on the VDS. You just say, I want to enable the control. And then there are 6 different traffic classes. There's NFS, iSCSI, vMotion, fault-tolerant logging, and management traffic, and then all the VM traffic. And then for each of these classes, you can set shares and limits. So the shares basically behave similar to like a CPU memory shares. It's like if you use DRS, you should already be familiar with the concept. And the limits are just the absolute limits a particular class of traffic can use. So for example, you can say NFS can use up to 2 gigabits per second bandwidth. Right? So you can look up the configuration guide for additional details. So there are a few additional things, just miscellaneous things I want to cover in the remaining time. So again, both the best practice and these considerations apply to VSS and VDS only. There's a separate session on Nexus 1000V that if you are interested, you can go to that session or just look up the slides they have. So one is the first point I want to touch on is the physical switch setup. The key point is that you don't need to worry about spanning tree protocol. The reason is that we do not, the virtual switch never forward traffic back out from one pNic back out another. Basically, vSwitch, adding the vSwitch is never going to add new loops. So here's the vSwitch allows you to forward the traffic between two vNics, and it also allows you to forward the traffic from a vNic to a pNic. But we never allow this type of thing. We never allow traffic to go from one pNic to another. And we don't allow traffic between vSwitches either. So you cannot go this way. So by preventing this, we don't add new loops. So we don't participate in the spanning tree protocol. And in terms of the physical switch setup, you basically leave the spanning tree on for the physical network and just turn on port fast on the ports that's facing the ESX side. And you can use BPDU guard to enforce the spanning tree boundary. A few more things on the physical switch setup. So on the VLAN, you want to trunk all the VLANs that might be used on the adapter. You should consider VMs that may vMotion into the host. That is, any VLAN that you can potentially use, you should trunk them all. Okay? If you only trunk the VLANs that's currently on the host, then you're going to run into a problem when a vMotion is triggered or a HA failover is triggered. Right? So you want to trunk everything. If you configure Ether channel on the physical side, remember it's a static only. There's no LACP. Okay, don't do that. And if you configure Ether channel, then on the virtual side, you have to configure IP hash. Okay. If you do anything else, then you're going to run into problems. Link state tracking. So some physical switches allow you to configure, say, if a downstream link fails, then you are going to signal the link down on the ESX facing side. So if the physical switch supports that, you should enable it. Okay? But if the physical switch does not have the link state tracking feature, then you can consider using beacon probing on the virtual switch side. Okay. Jumbo frame. So on the right now, in order to set up jumbo frame, you have to make sure that the MTU setting is set end to end, not just on the physical switch, not just on the virtual NIC, not just basically there are multiple places you have to set it. So for the VDS, you have to set it on the MTU, set the MTU on the UI, on the vSphere UI. For the standard switch, you have to use the command line. You have to set it on the virtual switch side. You have to set it on the physical adapter. And typically, the setting of the physical adapter is automatic once you set the switch. But you should check. You should check for errors. You also need to set it on the virtual adapter. And when you test if something is working, remember that when you ping with a large message, you have to specify down fragment. If you just ping with a large message, the IP layer is automatically going to fragment. So the ping going with a large message going through doesn't necessarily imply that you have configured the MTU correctly. Okay, so if you specify down fragment and the package goes through, that means the entire thing went through as a single chunk. Picking a virtual adapter for VMs. So we support a number of virtual adapters. I'm not going to go through them all. But the key here is that you should pick VMXNet 3. That's the latest generation, if available. I think the VMXNet 3 driver is not available in some of the older OS types. And if it's not available, you should pick either E1000 or VMXNet2. So finally, I just want to mention briefly here, you should consider using vNetwork appliances. Okay. By that I mean that a lot of the, the firewall solutions, load balancers, and all those things today are typically, resizing in a physical appliance. And VMware has started to build a framework to allow the security type of solutions to be built inside the hypervisor. And the way we do it is that between the VMs, vNic, and the virtual switch, we allow people to insert a filter in there. So with this filter, you can check, you can sort of drop packets, you can modify packets, and so on and so forth. And this allows partners to build security solutions. So we already have, the VMware vShield is partially built on this architecture. We have Reflex, Altor, and Checkpoint, and other partners who already have things in the marketplace. And there's a session on the vNetwork, the future directions of virtual networking, where you can get more information about the virtual solutions. And there are a couple of related sessions. There's a VDS deep dive, and there's also the Cisco Nexus switch on that. So that's it. Thank you.